Okay, you guys, our first video in this unit concerned the different forms of the quadratic equation and how how the same parabola could have a bunch of different ways that the equation looked, and each form gave you different pieces of info about that parabola. Today we're going to talk about taking a basic parabola, y equals x squared, and translating it, shifting it, flipping it, stretching it, moving it all around the coordinate plane, and how it can take different forms, and what we need to do to the equation to give it those forms. So we're going to start with just y equals x squared. Basic quadratic with, just taking your x coordinate and squaring it. So when x is 1, y is 1. When x is -1, y is 1. 2, 4, -2, 4, 3, 9, and so on. Okay, a couple features of this graph. It's even, meaning it has y-axis symmetry. It's even. The reason they're called even is because of the 2. A quadratic is even. Technically, it's even because if you plug in an x and you plug in the opposite of that x, like 2 and -2, you get the same height. Okay, no matter if I plug in a plus or a minus x value, I get the same height. That's called even. So what I want to talk about first is shifting this graph. How I can move this graph left, right, up, and down, and what I need to do to the equation to make that happen. So let's start with y equals x minus 3 quantity squared. What you need to know about translations, and these translations will apply to all types of graphs, but since our first unit is on quadratics, we're going to talk about them in depth here, and then we'll just come back to it when we get to different types of graphs. Changes that happen to x in the parentheses. This happens before I square to get my y value. These are horizontal changes. X minus 3 squared, this is a horizontal shift. And as you'll see a lot of times with horizontal changes, they act the opposite way of the sign. As in, x minus 3 is going to actually move this thing 3 in the positive direction. So that point right there, my old vertex, got moved 3 units to the right. All right, think about it. If you plug in x equals 3, I get 3 minus 3 equals 0. Square that, I get 0. Every single point on the parabola, all the ones that are shown and all the millions of points in between, they all get shifted 3 units to the left. All right, so that point right there, 3 units left, 3 units left. And what happens is if every single point in the parabola shifts 3 units left, then the whole thing shifts 3 units left. Vertical changes happen outside the parentheses. They happen to y, as in x squared. Actually, I don't even, if I'm just going to have a vertical change, I don't even need to have the parentheses. X squared minus 4. This is a down 4 movement. So my original, I'm not doing the 3 to the right. I'm doing 4 down from my original yellow. So if I move all of those points down 4, this is the parabola that I get. All right, so just one point at a time, the whole parabola moves down 4. And now you can have an equation that combines those two things. We've actually seen this already. Last video, you learned about vertex form. A vertex form is just the original parabola y equals x squared, but it's shifted left, right, and up or down. So let's say x plus 7 squared plus 1. All right, so this is the parabola x squared. Now, I haven't made it skinnier or fatter yet. I've just moved it twice. I have a plus 7, which is a left 7 and an up 1. As we start to get deeper into translations, we will move these things lots of ways and combine the flips and the shifts and the stretches and the shrinks and all that stuff. For now, we're just going to move it left and up. So my vertex, as you would have learned last time, is at -7, +1. Right here. And then I just kind of keep my same pattern. This point right here, 7, 1 lands right there, and so on and so forth. So I could have just a horizontal shift like the light blue, I could have just a vertical shift like the pink, or I could have a combination of two shifts like the white. But remember, whatever happens to the x is horizontal, and it's the opposite of the way it looks like it should go. What happens to y is the direction that it looks like. -4, that's a down 4. +1, that's an up 1. +7 is actually left 7 because it goes in the opposite direction of the sign. Okay, let's talk about flips. Again, starting with our original, y equals x squared. All right. Flips, this is not the best term for it. Reflection's probably the better term. But basically with parabolas, because we talked about them being even, already having y-axis symmetry, if I were to make this negative x squared, would you agree that y equals negative x squared is the same thing as just x squared? Oh, excuse me. Let me change that a little bit. If I were to make this negative x squared, that's the same as x squared. Because when you square a negative sign, that negative sign just goes away anyway. So we don't really need to deal with horizontal flips in this case, because if you flip a parabola, it's the exact same parabola. Now, if I were to move this parabola over and then flip it, like if I moved it right, and then I flip it over the y-axis, it would go over here. But usually they're not going to do it that way because it's easier, rather than moving it and then flipping it, it's a lot easier to just move it left in the first place. So technically a parabola could have a horizontal flip, but it's very rare. We're not really going to worry about it. More often we're worried about vertical flips. So let's do a vertical flip. Negative x squared. The negative is not in parentheses, meaning it's not getting squared. All right, so what happens is you square the value just like you did in the yellow version, then you make it negative. So what happens here is we get the mirror image over the x-axis. It flips down this way. So vertical flip, vertical reflection, it's a reflection over the x-axis. All right, no big deal. When you see a negative at the start, when the quadratic term when the quadratic term is negative, that parabola is going to open downward. And we talked about that in the last video. So let's combine the ideas. Let's try negative x plus 2 squared minus 3. So what things are happening here? We've got a shift of left 2, a shift down 3, and then a flip over the axis. All right, so my vertex is going to be -2, -3. I'm just basically treating this thing like vertex form. And you can approach these in several ways. You don't have to think of it in terms of translations. You can think, hey, I recognize this as vertex form. It's -2, -3. That's my vertex. And it opens downward. You can approach it that way. I haven't stretched it or anything, so I still have that kind of 1, 1, 2, 4 width to the thing, if that makes any sense. And remember, whenever you're graphing, and we will graph a lot this year, the final picture needs to be all the points that make the equation true. So sub in a value and see what you get. When I have x equals 0 in this case, my dot is down here at -7. So plug in 0 and see what you get. 0 plus 2 is 2, squared is 4, -4 minus 3 is -7. Always check your graph if you're the least bit unsure. Make sure that all the points that that graph touches make the equation true. All right, so let's get to the shrinks and stretches. I'm going to again start with my original. Now, some textbooks and some teachers will do horizontal shrinks and stretches and vertical shrinks and stretches. Basically, I'm going to just keep it vertical. If I were to change this and let's make every point half as tall as it was. So the 1, 1 will become 1, 1/2. The 2, 4 will become 2, 2. The 3, 9 will become 3, 4 1/2. So I just took every dot and I brought it halfway down. You could consider that to be a vertical shrink, like I'm squishing it vertically, making it wider, shorter, and fatter. Or you could consider that a horizontal stretch. I'm pulling on the sides and making it wider. We're just going to stick with the vertical, all right, because there's a couple ways to express what just happened there. 1/2 x squared. So I calculated the squared values, and then I just made them half as tall. The y value ended up being 1/2 of the original x squared height. And I would consider that to be a vertical shrink, all right? I have a decimal number less than 1, 1/2, and so I'm making the heights, the values, the y values, less than they were because I'm multiplying them by a number less than 1. This is also, and it's kind of an awkward value, but think of it like this. 1 over the square root of 2, x squared. Now that's something happening inside the parentheses to the x, which should make you think, hey, this is a horizontal idea. So a small number happening inside the x is actually a stretch. So that's pulling it on the left and the right and pulling it out wider. But again, you're not going to see it, just like you won't see a negative inside those parentheses very often, you're also not going to see a constant inside those numbers getting squared. We're just going to write it like this. So I have a vertical shrink in place. All right, I could also have a vertical stretch. All right, if I had y equals 2x squared. Y equals 2x squared takes those original points and it multiplies them by 2. Notice I'm not moving it, so if I take the origin 0, 0 and I multiply that by 2, I still say it's 0. But 1, 1 becomes 1, 2 because I'm multiplying the y coordinate by 2. 2, 4 becomes 2, 8, negative 2, 4, negative 2, 8. So here is a vertical stretch of 2. And again, I could rearrange that and make it a horizontal shrink by putting it inside the parentheses, squared 2x squared. Same thing, right? But I'm not really worried about horizontal shrinks and stretches. I'm just going to do vertical, and we'll just have a shrink and a stretch, and we'll know that that means vertical. Okay, so let's put all that together with one big example. Okay, so here's an example. Kind of puts all three types together. And again, if you look at this and think, hey, this is vertex form, let me find the vertex, let me flip it over, and let me make it 1/4 as tall, that's fine. All right, I'm giving you options here. I'm not trying to change what you learned in the last one. But let's approach it with translations. So let's list what are the things that are happening here. We've got a flip, so this thing's going to open downward. We've got a vertical shrink, times 1/4, meaning however tall, in this case going downward, but however far down those points would have gone, they're going to go 1/4 that distance downward. And then that x plus 3, remember plus 3, it's the opposite. I'm actually going to go left 3, and I'm going to go up 2 to get my vertex. Now, order of operations can come into play. What you don't want to do here is well, I'm not going to graph this one yet, but just as another example, let me just put it this way. You want to shift last. Imagine you have a vertical shift and a flip. So if I have this parabola and I want to flip it vertically and I want to move it up 4. Flipping it vertically makes it go like this. Moving it up 4 makes it go like this. The opposite of that, or the opposite order, would be moving it vertically and then flipping it all the way over the axis down here. So I have that one versus that one. And I know that kind of made a mess, but my point is shift last. Order of operations, addition, subtraction come last, right? So we're going to shift it last. So what I want to do is flip the thing, vertically shrink it by 1/4, then move it to the vertex. All right, so flipping it and shrinking it. I'm going to kind of go step by step. The original parabola was here. Flipping it puts it down here. Shrinking it. So let's see, 4 becomes 1. 1 becomes a fourth, so it's barely off the axis right there. I was at 9. 9 would become like, what, 2 1/4, 9/4, 2 1/4. You get the idea. This thing's going to get pretty wide. Doesn't have to be perfect. And now I want to move it up to its place. So let's take that thing, move it left 3 and up 2 to get our final answer. Left 3 and up 2, and then I'm going to kind of make that wide parabola like that. So final answer looks like that. It's kind of a rough sketch, but you get the idea. All right, but shift those things last. If you're approaching it in terms of translations, flip it, shrink it, stretch it, and then shift it at the end to stick with your order of operation. And most importantly, remember this all year long, wherever graph you draw should go through all the points that make this equation true. So check some points, make sure it's true, and you should be in good shape. All right, so that's translations. This is a big topic. We're just getting started with it on quadratics. Young out.